Hey guys, so we're going to do a little work with binary numbers. Let me share my screen with you. Start our slideshow. So we're going to look at how binary code works, and this is nothing more than counting in base 2. Take you back to Roman numerals for a moment. You might have looked at them a little in math in grammar school. So the question is, how would you read this particular Roman numeral, MMDCXIX? Well, it has several components. M is the symbol for 1000, so MM is the symbol for 2000. DCX, well, D is 500, C is 100, and X is 10. So DCX is 610. And then IX, well, the I is worth 1 and the X is worth 10, but the placement of I before the X indicates that it's subtracted from the 10. So 10 minus 1 is 9. So IX is 9. So when you add all that together, DCX, IX, you get 2000 plus 610 plus 9, or 2619. Now, in Roman numerals, the order of symbols is significant. Normally, symbols are arranged from the highest value to the lowest value, left to right, in decreasing value. But when a smaller value precedes a larger one, we subtract it from the larger value that follows it. And there are rules about what you can subtract from what. You can't subtract 1 from 100 and get 99. You'd have to have 90 plus 9 to do this. So you would have XCIX in that case. Complicated, I know. So take the value MCMXLIV. So the M is 1000, CM is 100 away from 1000, or 900. XL is 10 subtracted from 50, or 40. And IV is 1 subtracted from 5, or 4. So you get 1944. Now, the place you're probably most likely to see Roman numerals like MCM, XLIV is on movies. So, for example, if you were to watch any of these movies from the year 1944, you would see either in the opening credits or the end credits the year the film was made in Roman numerals. Some real classics here. All right. Working with Roman numerals is cumbersome. Simple math operations like subtraction, multiplication, division are very difficult using Roman numerals. So, for example, if we took MCDLXII and we subtracted CCXXXVIII, what is it? Well, to be honest, it's probably easier to convert these numbers to decimal and then do the math using Arabic numerals. It wasn't any easier for ancient Romans to use this math, so they didn't do those kinds of large subtraction problems. Now, when we work with decimal numbers, the type of numbers we're most familiar with, decimal is base 10, right? Everything is based on a power of 10. And we use 10 Arabic symbols as numbers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 as our symbols in decimal or base 10 using Arabic numerals. The number 1,024,512 can be parsed into different values. So first of all, we have 1 million plus 20,000 plus 4,000 plus 500 plus 10 plus 2. Now, another way to think of the number 1,024,512 is 1 times 10 to the 6th power, that's a million, 0 times 10 to the 5th power, 2 times 10 to the 4th power, 4 times 10 to the 3rd power, 5 times 10 to the 2nd power, 1 times 10 to the 1st power, and 2 times 1 to the 0 power, or 10 to the 0 power, and that's 2 times 1. Now, each place from right to left, if you will, represents the next highest power of 10, right? We started with 10 to the 0 power, the ones place. Then we went to the tens place. That's 10 to the first, 10 to the second is the hundreds place, 10 to the third is the thousands place, and so forth. Now, the order of symbols is very significant, right? Because 2,145,120 has the exact same digits, but it's not the same thing as 1,024,512. The order of symbols is significant. The places those symbols represent is significant. Now, the 0 has meaning. It's a placeholder in our original number here for the 100,000s place. There are 0 100,000s in this number. Now, when you're doing simple math operations, numbers can be placed so that their places are aligned vertically. So if you had 6,000 and you want to subtract that from 142,324, you'd put 142,324 on top. You would line the 6 with the 2 in 142,000. You would line the zeros up with the 324. And then that becomes a very simple problem for us to solve. We're subtracting the ones place from the ones place, tens place from the tens place, hundreds place from the hundreds place, and so forth. So this idea of positional notation, that we have certain places or positions and the numbers fit in those places, and that's very significant, is important to the way that we calculate using Arabic numbers. Now, binary numbers are based on powers of 2, not 10. But there are many things about binary numbers that work exactly the same way as with decimal numbers, including positional notation. We use the 0 as a placeholder, and we have increasing powers of 2 from right to left, 2 to the ones place, 2 to the second place, 2 to the third power, 2 to the fourth power. And we can align our places when we perform operations to make the math very simple. We even have things like borrowing and carrying, as you would in addition and subtraction. Now, because binary numbers are based on powers of 2, there are some differences between binary and decimal notation. Place values are different. Each new place has a value that's 2 times bigger. So if you are looking at the 4's place, the next highest place is the 8's place. The next highest place is the 16's place. There are only 2 symbols. We don't use the symbol 9 or the symbol for 7. We only have 0 and 1. Now, when you only have 2 symbols, binary numbers can be represented by a set of switches. Either the switch is on, that would be a 1, or a switch is off, and that can be a 0. That makes them ideal for computers and digital signals like MIDI, digital audio, JPEGs, and all kinds of things. Each switch in a binary notation is called a bit, and that's short for binary digit. And we group those bits into sets of 8, and we call those a byte. And it's literally short for the words by 8. Now, bytes can be further grouped into words, units of data, which have meaning that depends on the context. For example, we might see a value that's like this: 1001, 0010, 0100, 0001, 0110, 0100. Now that in MIDI would be a note on message on channel 2. It will play the note E3 with a velocity of 0. Now, that could also be a color in a JPEG. And in this particular case, it's the color maroon. Now, we could take a byte like this one, 1101, 0101, and we can parse that into separate components. So what do we have? We have a 1 in the 128th place, a 1 in the 64th place, a 1 in the 16th place, a 1 in the 4th place, and a 1 in the 1's place. So we just add those values: 128 plus 64 plus 16 plus 4 plus 1, and we get 213 in decimal. Right? So another way of looking at that in binary is 1 times 2 to the 7th, 1 times 2 to the 6th, 0 times 2 to the 5th power, 1 times 2 to the 4th, 0 times 2 to the 3rd, 1 times 2 to the 2nd, 0 times 2 to the 1st power, and 1 times 2 to the 0 power. So the place values are all powers of 2. It works just like decimal in that respect. Right, and here are the place names: the 128s, the 64s, the 32nds, the 16s, the 8s, the 4s, the 2s, and the 1s. Now, the lowest value of a byte in binary would be all zeros, and that's going to be equivalent to 0 in base 10. The highest value of a byte in binary is all ones, and that would be equivalent to 255 in base 10. So the highest value of any word is 2 to the nth power minus 1, where n is the number of bits in the word. So if I have a 24-bit sample, then the highest value would be 2 to the 24th power minus 1. And that would tell me how high I could count with 24 bits. As an example, a 16-bit audio sample would have to fall within the range of 0 to 2 to the 16th minus 1, or 0 to 65,535 in decimal. If you need a larger number, you add more bytes and you get more bits. Now, binary uses base 2. It's not base 10. It uses positional notation like base 10, where each digit has a particular place value. Places have values equal to powers of 2. And there you have it. That's how binary numbers work. And they're very useful. Again, the most important thing to understand is that a binary value can be expressed by a switch. And computers are nothing more than huge collections of switches. So that makes it very easy for them to work with binary numbers. That's it for now.